For part 6.1 of lab 20, so part 6 is applications of the analog switch, actually, which are pretty cool. So part 6.1, first application, is sample and hold. A sample and hold is actually a circuit that's quite useful in analog to digital conversion, which is basically getting a real world voltage signal into a computer. And so we will see this again pretty soon when we do analog to digital conversion. So basically we have an input signal. Or I'm going to say we have a sinusoidal input signal. Okay. So we have an input signal, and we want to freeze it for long enough to look at it. So let's say I want to know what's happening here. Well, let's say what's happening here, what's happening here, what's happening here, what's happening here, 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 here. Okay, so I want to ask myself what is happening at these discrete points in time. And what does what's happening mean? It means I'm going to say, look now. And I'm going to say, okay, and that's what I capture. And then I'm going to say, okay, look now. And that's what I capture. And I'll say, okay, look now. And that's what I capture. And then I'll say, look now, that's what I capture. 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 Look now, look now, look now, look now, look now, and so on. So I've basically sent the little go signal. I say here, go, 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 go. It really should be periodic in time, but I didn't draw very well. Okay. So yeah, these really should be evenly spaced in time, and they normally are. But, you know, when the little yellow signal comes by, you say, okay, I want to freeze the contents of the salmon-colored signal here and preserve it in this, well, to me, this looks light blue or kind of bluish gray. I'm not sure how it looks to you. A capacitor is a device that can remember the charge that you put on it. So here's the idea. Every time we get a yellow go pulse, we close the switch. Charge flows back and forth until the voltage on the top of this capacitor equals the signal voltage. And then we open the switch, and now that voltage stays there. And that would be fine, except we want a way to look at it. We want a way to look at it. And normally what you look at it with might be like an oscilloscope probe. But an oscilloscope probe is not a perfect voltage probe. It has like a 10 mega ohm input resistance. And if this is only 100 picofarads capacitance, then what's the RC time constant there? I guess we could work that out. So this is 10 to the 8th ohms, 10 to the 7th ohms, 10 to the 7th ohms times, and then 100 picofarads, that's like 0.1 nanofarads, that's like 10 to the minus 10 farads. Yeah, 10 to the minus 12 times 100. So that is like 10 to the minus 3 seconds. Yeah, so see, you could sample, but if you look at it with a scope probe, the charge will bleed away with an RC time constant of like a millisecond in this case. So maybe we want it to stay for longer. So we have here a follower, and this is not just any follower. This is a follower made with a JFET input OpAmp. So this is an OpAmp, and its inputs are FET inputs. So the bias current of this OpAmp is teeny. So we have a follower made with this is not your 741. This 411 has a really tiny think like picoamps or tens of picoamps bias current. So, so then you can look over here with the scope probe without perturbing the charge in the capacitor over here. So that's pretty neat. So I see this is a actually really useful use for a follower. You want to be able to look at a signal with a scope probe without affecting it. So you say, okay, I'll connect the scope probe over here, and then this is a very, very high impedance voltage probe, the input to this FET input OpAmp. So this gives me a way to observe the signal without disturbing it. So we have to remember how to wire up an OpAmp. So pin 7, this is the same pin out as a 741 OpAmp. Pin 7 goes up to plus 9 volts. Pin 4 goes down to minus 9 volts. Negative feedback from pin 6 back to pin 2, and then the input signal goes to pin 3. Here's a 100 picofarad capacitor. And then we're using the DG403 analog switch. So here's pin 16 and pin 1. These correspond to this source 1, drain 1 switch here. And then the logic that controls the switch is pin 15. This says use a manual switch. I thought it was more interesting to use like a waveform generator. And I wired this up, but I forgot the capacitor. I'm going to fix that. Okay, let's see how this is wired up. So we have the DG403 on the left. We have the LF411 OpAmp on the right. Let's start with the OpAmp. So pin 1 we don't need. Pin 2, we have a negative feedback from pin 6 back to pin 2. So that's this blue wire. Pin 3 is the signal coming in from pin 1 of the DG403, so that's this blue wire. And then pin 4 is our negative power, that's minus 9 volts. Pin 5 we're not using. Pin 6 we talked about. Pin 7, oh no, this is also pin 6. We're watching pin 6 with scope channel 2, which is going to be the blue or cyan colored channel. Pin 7 is plus 9 volts power, and pin 8 we're not using. Okay, then the connections in the DG403 are pretty much the same as the previous video. So, okay, so most of the action is pins 1, 15, and 16 here. So we have the powers, so 9 volts ground, plus 5, minus 9. Minus 9 ground, plus 5, minus 9 ground, plus 5, plus 9 are 14, 13, 12, 11. You want to remember to connect pin 10 to ground. It's an unused logic input. And then really the interesting stuff is 1, 15, and 16. So we have our signal going into pin 16. So that is, okay. For whatever reason, I made those connections over here left over from a previous circuit. So this blue wire is AWG channel 1, which we'll see in a moment is a sine wave. This green wire is scope channel 1, the yellow scope channel. So we're just watching what we're sending in. And then this little blue wire is jumping over to pin 16. Okay, so then if the switch is closed, then pin 16 gets connected internally to pin 1. So pin 1 of the DG403. It connects to pin 3 of the OpAmp with this blue wire. So that is our FET input follower, FET input OpAmp follower, which is allowing us to make use of the output of our sample and hold without perturbing it. And then this is a 100 picofarad capacitor from pin 1 of the DG403 down to ground. I think that's all we need to know there. Oh, and then pin 15 of the DG403 is telling it which mode to be in. So this says use a manual switch, but I decided it was more fun to use a second channel of the function generator. So the second channel of our arbitrary waveform generator, and I'll show you in a minute what I do with that. Okay, so let's look at the waveforms window. Power power supplies, as usual, +9, -9, and +5. I'm using 2 channels of the waveform generator. They're not synchronized to each other. So channel 1 is a 99 hertz sine wave, 5-volt amplitude, no offset. It could be pretty much whatever you want, I think. Channel 2 is a pulse. Okay, so it's kind of like a square wave, but it's asymmetric. It's a pulse, 1 kilohertz, so it comes once per millisecond. It's 5 volts tall, so it goes between 0 volts and 5 volts. So for a pulse, I guess the amplitude is the maximum value and the offset is the minimum value. And then it's 5% symmetry, so it's only on 5% of the time. All right, now let's look at the scope. So the magenta, channel 3, is our pulse. That's like scope channel 2. It's like the go signal. It's like this yellow go signal in the first drawing that I drew on the board here. And then this yellow trace, channel 1 of the scope, is our sine wave. That's our input signal. It's like this thing I drew here in pink. And then the cyan or blue curve, channel 2, is the sampled value. So that's kind of neat. So you see every time the go pulse comes, then the sample and hold remembers the value of the yellow curve and it keeps it until the next go pulse. Can you see that? So basically, the blue curve grabs the value of the yellow curve when the go pulse comes, and it keeps that same value until the next go pulse comes. So then the next question you might ask is, well, how good is this circuit at actually remembering the value? So maybe there's some non-zero slope to this blue curve. So I think what we're going to try to do is sort of zoom in and see what is that slope. And I think what you're going to see is the tiny bias current of this 411 OpAmp. Let me see. So I guess if we say I equals C by dV, yeah, I equals C dV dt, right? So Q equals CV. We take the derivative of the Q is I and derivative of V is dV by dt. So then that gives us dV by dt, right? So dV by dt is, it's going to be basically the bias current of the OpAmp divided by this capacitance. Yeah. So let's see if we can estimate the bias current of the OpAmp that way. So if we zoom in on one of these waveform portions, let's see. I guess we can change our time scale. But also, I think I'm going to trigger on the yellow curve at a higher point. Like maybe I'll trigger on the yellow curve at, well, I could say 5 volts. I think 5 volts won't happen very often. Let's try 4 volts. Okay, that's good. Trigger on the yellow curve at 4 volts, and then let's zoom in time here. Maybe I'll trigger on the yellow curve at 4.5 volts. Okay, so I guess maybe you can see a tiny little bit of a slope here. Yeah, I think maybe you can. It's hard to tell. So I guess we don't have to be too precise. We just want an order of magnitude here. So let's use the cursors. And this looks like channel 2, 3.12 volts. Channel 2, 3.105 volts. Oh gosh. So that's a pretty small change. Maybe let's make something a little more convincing. You know what we can do? Let's go back to WaveGen. And let's, first of all, why don't we make these things kind of more coherent with each other. And then let's sample less often. So I can make this 10 hertz, and let's sample at 100 hertz. Yeah, okay. And then let's synchronize them. Okay, let's see what happens. Okay, so now we need to zoom out in time. That seems pretty good. How do I delay? Let's see. Let's move over a little more. That might be pretty good. So if I stop this, cursor says channel 2, 4.96, oh no, channel 2, 4.819 volts. Here, oh, channel 2, oh, no, that's no good, 4.908. It looks like it hasn't changed. I mean, it's obviously not really going up, so it hasn't changed. G. Okay, maybe this is why Tom asked for a manual switch, because we really want to do this very infrequently. I could, all right, I think I'm going to take basically a constant input, and then I'm going to sample it and see how long it takes to go down. Let me set that up. Okay, I think now we can see what's going on. So I set things up so we are sampling every 5 seconds. That's 200 millihertz. So we're sampling, no. Oh gosh, that's wrong. We're sampling once per second. We're sampling once per second, 1 hertz. And the waveform that we're sampling is a 200 millihertz square wave. Okay, so it's, what does that mean? That's 5 seconds. I guess it's high for 2.5 seconds and it's low for 2.5 seconds. Okay, so let's take a look at that. So then I just captured one trace. So the magenta, or violet magenta, is the go signal. Okay, so the go signal comes once per second. Okay, so it's 1 second per box here. And then the yellow signal is what are we sampling? So it's high for 2.5 seconds, it's low for 2.5 seconds. Okay, so it's 0, right, oh, okay. It's minus 5 volts for 2.5 seconds, then it's plus 5 volts for 2.5 seconds. It's minus 5 volts for 2.5 seconds, and so on. Okay. Then let's look. Then let's look at the. Then let's look at the cyan trace, or the kind of light blue trace, which is up here. That's our sample. Well, actually, we're not really looking here because that would be that would drain the capacitor too fast. We're really looking at the output of the follower, but we're inferring what's on this capacitor. Okay, and when we do that, we see that in 1 second we go from, let's say, 5.1 volts down to 4.0 volts. Let's just call that 1 volt, okay? So we have dV by dt is 1 volt per second. Okay, so 1 volt per second is approximately I bias over 100 picofarads. So that gives us I bias is like 100 picoamps. Right. Okay, and I think that's of the right order of magnitude. I could look that up for you. LF411 I bias. Amazing. I look at the LF411 datasheet and it says input bias current, typical 50 picoamps, maximum 200 picoamps. And we have something on the order of 100 picoamps. And this is like an order of magnitude estimate. Cool. Okay, so you kind of see, we were like grabbing the sine wave. We want to save the sine wave long enough to look at it. So we use the capacitor to keep, right? So you close the switch and you keep on the capacitor that voltage. You open the, you close the switch, charge flows onto the capacitor or off the capacitor, so this voltage is the same as this voltage. Now you open the switch, and it stays there as long as there's no current flowing in or out of the capacitor. So you use this OpAmp with a very small bias current so that you can look at the answer on the capacitor without disturbing it. And you say, well, how long does it stay that way? And you say, well, it depends on the bias current of the OpAmp, and it depends on how big a capacitor you used. Okay, so I think you can follow that. That's cool. Oh, by the way, so Tom has this question. Can you infer from the droop of the signal when the switch is in the hold position what leakage paths dominate? Well, so I think the answer is it's I bias of the 411 OpAmp. And, well, let's just suppose that it is. Then it kind of makes sense because we got, I mean, our dV by dt is consistent with what you expect from the bias current. Now, what if so the question is, could there be some other, so it seems like the bias current of the 411 is sufficient to explain the dV by dt that we see. Is there some other leakage path that might make sense? And I guess we didn't check what is the resistance of this analog switch when it is open. So we checked the resistance when it's closed. We didn't check the resistance when it's open. So I'm not sure how to quantify that with what we measured already. But anyway, I think this is an adequate explanation. Okay, I mean, I guess in principle we should rule out other explanations, but this seems pretty good. So I'm going to end this video and then move on in the next video to part 6.2, which will be the chopper circuit.